Welcome to the OK Let's Learn podcast. This is two podcasts in one. One where we dive into tons of interesting books and stories, and another where we dive into interesting topics. My name is Kevin O'Keefe. So today, let's learn all about thunderstorms, explaining why, how, what are the conditions that a thunderstorm will all of a sudden appear. This is being recorded in New Jersey in the summertime, and yes, you have your afternoon thunderstorms very often in the northeastern part of the United States, and certainly year-round down in Florida. Well, a lot of you may know, it's all about the humid air, and if you got a lot of humidity, that's the big recipe for thunderstorms, but there's so much more to know. So we will answer a lot of these questions. How does it start? It's a perfectly blue, beautiful day, white cumulus clouds, and all of a sudden, you got a thunderstorm, right? Why does the sky go dark? Where does the lightning come from? What causes thunder? And why all of a sudden does the wind suddenly become so strong? All of these ingredients, you think about a thunderstorm, you got so much here. You got the wind, you got lightning, you got thunder. Right? Massive downpours of rain. So we're going to dive into all of this. So it starts with the sun, right? And so much of this is the water cycle. You've got precipitation, you got evaporation, you got condensation, right? Around and round. Definitely go back to my episode on the water cycle. But in terms of the conditions to make the precipitation a thunderstorm, it still starts with the sun. As the ground warms, it begins heating the air directly above the ground. And warm air is lighter than cool air. So, with that being the case, as the air near the ground becomes warmer, it begins rising into the atmosphere. Meteorologists call this updrafts. And an updraft is simply rising air. Without this rising air, there's no thunderstorm. Now, immediately you may be thinking, why does warm air rise? Well, it's because its molecules are moving faster and they're spreading further apart, making the air less dense than the cooler air around it, right? When you're talking about density, you're talking about things being packed closer together. And that's what's happening with the molecules as the temperature changes in the air. Cooler air has molecules packed more closely together, making it denser and heavier. So gravity helps keep it near the ground, while the lighter warm air rises above it. Now, this is, again, we're going into a lot of details, so again, go back to my water cycle episode. But as that warm air rises and it climbs higher into the atmosphere, it expands and it cools, which is eventually what forms the clouds and obviously the rain droplets. That's condensation. You say, well, wait a minute. I thought warmer air is rising and, it's still always going to be warm. No, actually what's happening, and it becomes cooler because there's less air pressure pushing down on the molecules, so those molecules expand, but there's still the same number of molecules within a specific space, and they're still going crazy, right? But now, since they're further apart, they're exerting more and more energy, and for that reason, it gets cooler. It gets cooler because the molecules are slowing down. There's no new energy being added into that space. The molecules give up some of their energy, so they're moving slower. And temperature being a measure of the molecules moving, that's why the air is getting cooler. These understandings about the movement of air being warmed in and closer to the ground, and as it gets higher and higher, it obviously expanding and getting cooler is really the foundation of understanding ultimately precipitation. And now we go further into how this precipitation actually turns into a thunderstorm. Because the key ingredient, and we referenced this earlier, it's all about the moisture in the air, the amount of water in the air. That's called humidity, right? It's not about warm air being enough. There's got to be a lot of water in that air. On a sticky summer day, you can feel the humidity. It's like going into a sauna. It's like you can grab the air in front of you. It's just sticking to your skin. It feels so horrible. In the northeastern part of the United States, it gets humid during the summer because that warm, moist air is moving northward. Actually from, believe it or not, places like the Gulf of Mexico, the Atlantic Ocean. Here up in Jersey is coming from the Chesapeake Bay and obviously all the lakes and rivers. That moisture acts like fuel for what we're talking about here with the thunderstorms. The more humid the air is, the more likely it is that clouds and the storms can develop. It's all about the clouds being developed here with condensation, right? You got to think of humidity as gasoline for a storm engine. Without it, thunderstorms, they just don't happen. So now we get to the part where we talked about the rising, expanding air and it being cooler, right? Well, if you've got gas and you've got the water in the gas, which is the air, that's called water vapor, right? Well, now if those water droplets are getting cooler and cooler, right, with the expanding and the rising air, you've got a lot of that water vapor in the air. You're going to have more and more water droplets form, and this is what creates the clouds. This is condensation. And you know what? Fair weather clouds, they're relatively small. You can kind of see the big ones, the cumulus clouds, and then all of a sudden they're different, right? They can grow several miles high. And now you're talking about when you're looking at some of these clouds, really big, flying high in the air. They're known as let's see if I can get it, cumulonimbus clouds. And they can reach heights of upwards of 30 to 50 or 60,000 feet. They're actually, in some cases, higher than a lot of the airplanes, the jet airplanes will be flying. At the very top, these clouds often spread outward. So if you see almost like an anvil-shaped cloud with the width of the cloud being higher than, closer to the ground, you're seeing nature telling you that there's going to be a thunderstorm on its way. I mean, when I say an anvil, it's like a T, right? It's actually a cast metal block that you use, blacksmiths will use, and it's this actual anvil shape where now all of a sudden the sky's getting dark and say, what's happening here? Well, the answer is simple. These thundercloud storms are blocking the sun. And another thing you may be thinking, well, why is it that it's forming this anvil shape? Why is it spreading out? Well, at a certain point, the air is moving fast and it's rising, right? It eventually reaches a layer of the atmosphere, which is like a ceiling. And the rising air can't move any much higher. So it spreads outward instead. And then these high altitude winds carry the clouds sideways, creating this flat anvil shape cloud. That flat top of the anvil where the ceiling is actually called the tropopause. This boundary separates the troposphere from the stratosphere. All of the Earth's weather happens in the lowest level of our atmosphere, which is the troposphere, otherwise known as the troposphere. This troposphere is where we live. It's where the clouds form and obviously where the storms develop. As a thunderstorm grows, the warm air rising eventually reaches that tropopause. Like I said, that ceiling. The reason it can't go much higher is that the atmosphere changes. How does it change? Well, basically, the stratosphere, which is that next layer, it's a lot more stable. The air is more stable and it resists the vertical motion of the rising warm air. It's basically like a giant invisible lid on a pot. When the thunderstorm reaches that lid, it can't go any further, right? So the clouds spread out. And again, this is fundamental to our talk here about the thunderstorms. Atmosphere has a huge impact on this. When you get to the stratosphere, when I said the air is now stable, well, that's because the temperatures stop decreasing. They actually begin going back up as you get higher, now reaching this part of the atmosphere. This happens because the ozone layer absorbs ultraviolet energy from the sun and warms that part of the atmosphere. This creates a situation where the air above may actually be warmer than the air below. So that's what we're talking about, the air becoming more stable. It's not about the warm air continuing to rise. Again, yeah, what's going on? You're digressing again. But no, again, this is important to understand. And certainly, no doubt future episodes on the ozone layer in terms of space, etc. Well, you go from the troposphere, which is generally speaking up in the Northeast, you're talking about 7 to 8 miles up in the air. Not 6, 7, but no, 7 to 8 miles up in the air. And that's when you reach the stratosphere. Then when you're about 30 miles up in the air, you're in the mesosphere. And then 50 miles, you're in the thermosphere. And believe it or not, the atmosphere doesn't stop. You go then to the what they call the exosphere, which is 400 miles and higher. And when you talk about space, you're basically talking about right there in the thermosphere, about 62 miles above the Earth's surface. That's when you're talking about space. And since we're here, commercial airlines are usually flying around 6 to 7 miles high. Yeah, I'm not going there. Thunderstorms, believe it or not, can reach 10 to 13 miles high. I mentioned space is 62 miles high, and the International Space Station, talk about space, they're actually 250 miles high in the air. So let's get back to thunderstorms. In these clouds that now you have developed, these huge thunderstorm clouds, they anvil, the air is moving in all different directions. You can kind of picture this, right? Some air is rising rapidly, some air is sinking, water droplets are colliding, ice crystals are colliding, tiny hailstones are bouncing around. This is what's happening. The cloud is like this enormous mixing machine. You got to imagine like a giant washing machine in the sky, right? Everything is moving, everything's colliding and spinning and swirling, and this leads to one of the most amazing phenomenon that we know as lightning. So let's dive into lightning now. Scientists are still studying, figuring out what's up with lightning because it's very detailed, and yeah, it's easy to observe, it's easy to recognize, but in terms of the basic process that develops lightning, you got to think of these collisions, right? So I mentioned the ice crystals, the water droplets, and actually tiny little hailstones. They create electrical charges. Some part of the clouds, right? Let's take one particular cloud. Some of that one particular cloud becomes positively charged. Other parts become negatively charged. Eventually, these charges become separated. The difference in electrical charges grow larger and larger. Nature wants to balance the charges. When these electrical differences become strong enough, a giant spark happens. That spark is lightning. Lightning is essentially a massive discharge of electricity. You got to think about the tiny spark that you see when obviously you touch a doorknob or you take that blanket out of your dryer, right? You're seeing like a little discharge of lightning, right? That's electricity. It's the same idea. Now that lightning bolt, talk about a fun fact, it's just crazy. That lightning bolt can heat the air to upwards of 50,000 degrees Fahrenheit. That's hotter than the surface of the sun. So talk about powerful. Now, this is not a podcast about chemistry and physics, although, again, we got a past episode on both that you can go back to. But you got to understand electricity if you're going to understand thunderstorms. So briefly, right, everything around us is made of atoms. I'm basically talking about how is it, we talked about positive charges and negative charges. Well, what does that mean, right? And that's how they want to balance out. What does that all mean? Inside those atoms are tiny particles called protons and electrons. The protons carry a positive charge, and the electrons carry a negative charge. Normally, most objects have about the same number of positive and negative charges, so everything stays balanced. They stay together. Well, sometimes the electrons move from one place to another. When an object gains extra electrons, it becomes negatively charged. When an object loses electrons, it becomes positively charged, right? You can kind of see that understanding of that balance being out of place. You got to think of it like a seesaw, right? Going from one side now, having too many electrons, while the other side doesn't have enough. If you've ever shuffled your feet, again, to just look at the metaphor and to understand the imbalance in where electricity is coming from, when you shuffle your feet against a carpet and then you touch a metal doorknob, electrons moved from one surface to another through friction. Your body built up an excess amount of electrical charge. When you touch that doorknob, the charges suddenly balance themselves with a tiny spark. That's static electricity. Again, I know we're digressing, but it's important to understand lightning is basically the same process, but at a huge scale. Inside a thunderstorm cloud, billions of water droplets, ice crystals, and like I said, these tiny hailstones are crashing into one another. These collisions knock electrons loose and move them around. Over time, parts of the cloud collect extra electrons and become negatively charged, while other parts lose electrons, and that's where the positive charges come in. Scientists are still trying to figure out all these details here, but the simple picture is the upper part of the cloud often becomes positively charged, the lower part becomes negatively charged. It's as if the cloud becomes a giant battery. Nature tends to prefer balance. When the difference between those charges becomes large enough, the air can no longer act as an insulator. Suddenly, electrons rush through the air in an attempt to balance the charges, and it's that enormous discharge that's electricity, which is lightning. Lightning in this case, right? It's essentially the atmosphere's like pressure release valve, if that's another good way of looking for this. It's a pressure release valve for electrical charges. Another analogy is basically like a dam holding back water. Well, when the pressure increases enough behind that dam, eventually the water has got to flow through the spillway or over the dam, right? Lightning is like that same release. And what's interesting is lightning doesn't always happen between the cloud and the ground. Sometimes it happens in the same cloud, between two clouds, obviously from the cloud to the ground, but occasionally, right, you can actually have the discharge coming from the ground to the cloud, or like I said, vice versa, because most lightning actually never reaches the ground. Most of it occurs within the cloud itself as the cloud is kind of messing with all these different charges. That's why you'll just kind of see the sky just light up. Yeah, well, we know that is lightning. It's just not that bolt that ends up going to the ground. So what about thunder, right? Thunder is really just the sound of that air exploding outward after it was heated by the lightning. The lightning comes first. A lot of people don't realize that. The thunder comes second, always. The lightning superheats the air around it almost instantly. The air expands like this big explosion, right? The expansion of the air creates a shock wave. That shock wave travels through the atmosphere as sound. The sound is thunder, right? Well, why is it that we see first the lightning and then actually hear the thunder? Well, light travels a lot faster than sound. Lightning flashes, they reach your eyes almost instantly. Thunder? No, because it's sound, it gets there later, right? Actually, a useful rule, you count the seconds between a flash of lightning and the thunder. Every 5 seconds between those roughly equals a mile away, and meaning that lightning bolt was a mile away, generally speaking, right? You're not measuring the distance to the rain or the center of the storm when we're talking about a mile away. Thunderstorms can be many miles wide, and lightning, please understand this, it can strike far from the heaviest rain. The bottom line, that's why meteorologists will say if you can hear thunder, you're close enough to be struck by lightning. You hear thunder, get out, go into your home. So now, what about the rain, right? We haven't talked about that. Thunderstorms is basically rain. Well, those tiny water droplets that are in the clouds, they collide with each other, and then they're getting bigger and bigger. Eventually, they become too heavy to stay in the air. That's when gravity takes over, and that's called precipitations. The droplets fall. In strong thunderstorms, updrafts are powerful enough to keep lifting droplets repeatedly. That's why they grow larger and larger before falling. And yes, that's why the thunderstorm rains often are coming down in buckets, in large drops, and you're talking about flooding, flash floods becoming a reality, right? Now, what about the winds? You're obviously talking about sometimes thunderstorms, very little wind, but sometimes, yeah, you've got massive winds, and that's when you're talking about hurricanes, you're talking about these nor'easters. Rain falls through the cloud. When it does, it drags cooler air downward. The meteorologists call this the downdraft, right? When that cool air reaches the ground, it spreads outward in all directions. The rushing air creates the gushing winds. Sometimes the cool air from the cloud can race ahead of the rain itself. You may suddenly feel a cool breeze. Leaves start moving, right? You can see this. We all know this. Approaching winds. Oh no, there's a storm ahead, right? Trees start moving. That cool gust is often nature's way and warning system that a storm is approaching. I mean, winds, and from a very simple standpoint, is just simply air moving from one place to another. And why is this happening? Well, just like water moves downhill to where there's places where there's less of it, right? Air is trying to do the same thing. So like I said, why is it the wind is involved with a thunderstorm? Well, the wind is just simply moving air, and in that thunderstorm, the cool air is rushing downward, and it spreads across the ground that creates the gust of wind that normally accompany a storm. So to wrap up our podcast, we kind of referenced this, but why is it that the summer afternoons are always producing the thunderstorms? Certainly here in the northeastern part of the United States, it's the perfect ingredients, right? You got strong sunshine, you got the warm ground, the humid air, and then the rising air. The atmosphere stores the energy throughout the day, and by late in the afternoon, there's enough energy that's built up for the storms to develop. That's why many thunderstorms in the summer arrive mid-afternoon and early evening. So why is it that some storms are just and others are really severe? Well, it basically is happening when there's additional ingredients that are part of the mix. And also when you talk about isolated thunderstorms, right? You see them on the radar coming across, and obviously some are more impactful than others in terms of the rain, in terms of the wind. Well, The other huge ingredient is something called wind shear. Wind shear basically means winds that change speed or direction as you move higher into the atmosphere. This can cause the storms to organize and strengthen. Severe thunderstorms may produce what we know, the frequent lightning, the flash flooding, even tornadoes, which is another episode. But fortunately, most of the thunderstorms never reach the higher level, but we've all experienced them. And why eventually do they peter out and die? They don't last forever, right? Well, eventually, these thunderstorms, for lack of the best way to explain it, run out of energy. This is what happens. The downdrafts, right, they become stronger. The cool air spreads across the ground, as we talked about. Well, that cooler air cuts off the supply of the warm rising air. Without warm rising air, the storm basically loses its fuel. The clouds weaken, the rains eventually decrease, the thunder becomes less frequent, and eventually the storm dissipates. The atmosphere pretty much has spent all of its energy. And then, hopefully you have some nice days, cool days, less humid days, but you've got the process that can start up again at any point. Talk about why meteorologists and weather forecasters have a tough job. Are you starting to get the idea? Now, finally, you've got to mention here something that's obvious. I've been talking about where I am in New Jersey. Well, throughout the world, you got thunderstorms, of course, but they're more prevalent in certain areas where the warm temperatures and humidity are more often, and they're occurring daily, let's say maybe around the equator. In deserts, storms are less common, obviously, because the moisture is limited. And finally, if you live in the Great Plains, the middle of our country in the United States of America, what about those tornadoes? No question, a future episode. But here, listen, thunderstorms almost always occur with tornadoes. These thunderstorms, they can become powerful enough to produce these tornadoes, right? Why in the Great Plains? Because you got this warm, moist air that's coming up from the Gulf of Mexico, and they frequently collide with the cooler, drier air from Canada or the Rocky Mountains. So these contrasting air masses, they're stuck right there in the flat plains of the center of our country, the Tornado Alley. Well, they combine with changing winds at different altitudes, and these thunderstorms begin to end up rotating, and obviously they can produce these powerful, horrible tornadoes, which no doubt is a future episode. Friends, thanks for joining me on this episode, learning all about thunderstorms, how they're created, what they're all about. I hope you have a better understanding and takeaways here the next time you hear thunder, the next time the buckets of rain are coming down, overnight or during the day. Reach out to me at kevmok21@gmail.com. We have a Facebook group. We have a YouTube channel. Any questions for future episodes? I'd love it when you follow the podcast. Hit that plus button in the top right-hand corner. Any comments via my email, any ratings and reviews through your podcast platform of choice. Always appreciated. Until next time, have fun and keep learning.